All right, kids. I know there have been some glare issues. I'm working with a slightly off-center camera today. Maybe it'll work a little bit better. I don't know. Working on this glare. I know the glare right here is a little wicked sometimes. Trying to deal with it. We are talking about section 3.2 today. So we did 3.1 yesterday. I know yesterday was kind of heavy on the vocab. A lot of things to make sure you wrote in your notes. So we're going to reference what those different definitions mean. Going to be some of that today. Not quite as long. And we're going to take today. We're going to break it over 2 different days of lessons. So. Does the graph represent linear or nonlinear functions? So linear means straight line, nonlinear means not a straight line. It doesn't have to be a curve, just not a straight line. Okay? So this obviously would be non-linear. This would be linear. That is a straight line. So it's pretty easy to tell if I show you a graph of linear versus nonlinear. Now, we need to be able to make that determination if it's not a graph, just given the information in different ways. So right here, what I look at when I'm looking at linear or nonlinear is what is the change, the rate of change. And if it's linear, the rate of change is consistent. So here we go. This is going down 6, down 6, down 6. Okay? Across here is going up 3, up 3, up 3. So the rate of change, we look at the change in y over the change in x is -6 over 3 for all of them. And it's consistent for each one. They're all in the same ratio. So then we come over here. So this one here is linear. B, 2 to 9. This one's going up 7. Up 11, up 15. Now that in itself doesn't disqualify it because we're looking at a ratio. So this is up 2, up 2, up 2. So the ratio here is 7 over 2. The ratio here is 11 over 2. Those are not equal, obviously. So it is non-linear. Okay? Now, that's pretty much all there is if they give you a chart like this to determine if something is linear or not. If it is the same ratio all the way across, that's linear. If it's not the same ratio, it's nonlinear. All right, so we take a look here. Number 1, is it linear or nonlinear? Quite obviously, number 1 is linear. It's kind of hard to read. Go ahead and just write them up here. Is this linear? Well, you might be thinking but it's not a straight line. It needs to be continuous, okay? So this, since it changes direction, is nonlinear. Come down here to number 3. Again, I got to look at all of these rates. Up 2, up 2, up 2, up 1, up 1, up 1, 2 over 1, 2 over 1, 2 over 1. That is a consistent rate of change, so that is linear. Here, down 8, down 4, down 2, up 1, up 1, up 1. So this is -8 over 1, -4 over 1, not equal non-linear. Constant rate of change, straight line. Not a straight line, not a constant rate of change. Linear, nonlinear. All right, so these are a little hard to read. I'm going to just rewrite these here real quick. You should be writing them down as well. How can you tell just by looking at an equation? Well, general rule of thumb, if there's anything weird in the equation, it's going to be nonlinear. What do I mean by weird? Things we don't see all the time. So, just one variable, whether it's an x or a y, that is linear. Okay? One variable is linear. Go ahead and write that down. When I said something weird, something you don't see all the time, a square root, we would consider that weird. You don't need to know exactly what it looks like, just something that's different. That is non-linear. The variable as an exponent, that is non-linear. Again, I don't need to know exactly what that looks like. I just need to know that's different, okay? This may not strike you as different, but it is a variable in the denominator. You should be making notes of all of these things next to all these problems. What makes them nonlinear, so when you see them again later, you know where to classify them. This is non-linear. All right? That. Parentheses aren't weird. We've seen a lot of parentheses. There's nothing weird here. There's no exponents. There's no variables in the denominator. There's nothing here that's a problem. That is a linear equation. All right, and down here, x squared. Again, not just variables in the exponent, but any exponent is going to give you a non-linear graph. Okay? So, make sure you have these down, make sure you have the classifications down, and make sure you wrote down the explanation that I told you, and you can do this in the future. So, linear or nonlinear, same deal. Same thing, not going to go through that. All right, so let's look at this. Different ways to represent a function. So we have words. An output is 3 more than the input. An equation that comes from there. A table, this is called a mapping, or obviously a graph. So there's lots of different ways that we can look at these things. We talked about how we can tell things are functions if I ask you, or I can just tell you that something is a function. We're going to be using these tables and graphs a lot in the very beginning here. So, I feel like I zoomed a little bit. 2 things, we touched on this yesterday. A discrete domain, set of input values, consists of only certain numbers in an interval. So the integers from 1 to 5. Think of discrete as whole numbers, okay? That's a good way to think about discrete. There's nothing between the values. It's just 1, 2, 3, 4, 5. Continuous domain set of input values consists of all the numbers in an interval. So this is 1, 1.1, 1.2, 1.3, 1. It's everything in between, okay? Discrete, continuous. Make sure you write these definitions down in your notes. Pause the video if you need to. I'll get my big head out of the way. Draw the diagrams as well. So, it's a little hard to read, but I understand. I'm not going to rewrite the whole thing. But it says a linear function represents the cost in dollars of X tickets. So, Y is the cost, X is the tickets. For a museum, each customer can buy a maximum of 4 tickets. Find the domain of this function. So, refresh your memory from yesterday. Domain is the inputs, domain is the X's, all right? Is the domain discrete or continuous? So first off, it says find the domain of the function. Well, each customer can buy a maximum of 4 tickets. So what values, how many tickets can you buy? Well, if it's a maximum of 4, how many can you buy? What are the options? Well, I can buy 0, I can buy 1, I can buy 2, I can buy 3, I can buy 4. If it's a max of 4, I can't buy more than that. Can I buy, and this, so there, that's A. Find the domain. I could write it like this, or I could write it as domain like we did yesterday. There's my domain. Those are the possible values that I could look for. Second part of this, is it discrete or continuous? So this is where you need to ask yourself, can I buy a fraction, or can my x be a part of a whole number? Can I buy a part? Can I buy a half a ticket? Can I get something in between the values? Because if you remember our definition, it says consists of all numbers in an interval. Well, can I buy everything between 0 and 4? Can I buy 2.5? Can I buy 2.6? No, obviously not. It's not continuous. It is only those whole numbers. So this is a discrete problem. Graph the function using its domain. So when I tell you to graph the function, that means you actually need to do the work. You need to take these values and plug them in to find your y. So again, x, y. If I plug in 0, that's obviously 0. If I plug in 1, that's 15.95. Get out a calculator, work on the rest of these values. I'm actually going to clean this up a little bit so I can have room for my graph. So, here's your chart. If I plug in 0, I get 0. If I plug in 1, I get 15.95. I plug in 2, I get 31.9. 3 is 47.85. 4 is 63.80. So those values now become coordinates. My x and my y, my input and my output become coordinates, and then we plot the coordinates. It is a discrete problem. So right here, notice there's no line connecting the dots, because when you draw a line, you're saying that I can go in between those values. You can't. I can't go to 1.5 tickets. There should not be anything there. Discrete means it's only the dots, only the points. It's not the stuff between. So this is what your graph should look like. Do a rough sketch. Obviously, this counts by tens. You don't have to get crazy specific or crazy accurate here. I'm not grading on accuracy. I would be grading on the fact that you have points, not lines, and that you have the general shape. Okay. Let's do one more of these. So a linear function m equals 50 minus 9d. I'll rewrite the problem for you. Represents the amount of money in dollars you will have after buying D DVDs. So going back to yesterday's, which one is independent and dependent? That's not up here, but let's talk about that real quick. Independent versus dependent. So where am I plugging in numbers? I'm plugging in numbers for D. That's my independent variable. M is my dependent variable. So my independent variable, where I'm plugging numbers in, if I would make a chart, that's my x. My dependent is my y. So remember, my independent is my input. My dependent is my output. All of these things are related. Independent, domain, all of that stuff is related. So question A says, find the domain of the function. What numbers can I plug in? Well, did it give me a restriction on this problem? No, it didn't tell me there's a maximum this time. It didn't tell me anything. So I need to plug it in and do the work and find out. Can I buy, what's the first number I can buy? Not 1, 0. 0 is an option. So if I buy 0 DVDs, how much money do I have? Well, I plug it in here, I do the work. 9 times 0 is 0, 50 minus 0. I have $50 in my pocket. Continue. Buy 1 DVD, plug it in here, I'm going to get 41. Keep going, because the question says find the domain of the function. So I keep going. I have more things I can plug in. Buy 2 DVDs, that's going to be 18, 32. Buy 3 DVDs, that's going to be 23. 4 DVDs, 14, right? Because 4 times 9 is 36, 50 minus 36 is 14. Buy 5 DVDs, that's 45. That gives me $5. Buy 6 DVDs, 6 times 9, that gives me negative $4. Can I buy 6 DVDs? No, I can't have negative $4 in my pocket. So now, the problem didn't tell me I had any restrictions, but reality sets in. I can't have that. So my domain stops right here. My domain is 0, 1, 2, 3, 4, and 5. That's the domain. Is the domain discrete or continuous? Can you have a fraction in your domain? Can you buy a part of a DVD? No. You either buy a DVD or you do not. So this is a discrete problem. Part B, graph the function using its domain. So, get this out of my way. I take these values and I make them into coordinates. I don't need an entire graph, so I'm going to rewrite that. I'm just going to look at this part of the graph right here. 0, 50. So that's 0, let's count by 10. 20, 30, 40, 50, right there. 1, 41. 1, 41. 2, 32. 10, 20, 30. 3, 4, 4, 5. So I didn't give myself a very good gap here. It's kind of a sloppy graph a little bit. Let me fix that so it looks better. So what you're gonna know is, and the reason I'm leaving this in the video, if you're sloppy, your graphs aren't gonna come out real nice. When you draw these by hand, try to get the distance between these lines consistent. If you're inconsistent when you're doing it, you're gonna have a problem. So if you're sketching these out by hand, note they should come out, everything's linear. Going back to our conversation from earlier, linear means straight line. Everything should come out to be a straight line. All right, we're going to continue with the word problems tomorrow. That's the end of the lesson for today. Domain, range, input, output, discrete, continuous, and make a graph.